other no users, they can also develop lung cancer. So there are many factors. So for example, take ABCD. So the culprit for the risk factors, ABC may cause. So that is the reason. Liver cirrhosis, in fact, we cannot say it as a risk factor. It is a more liver cirrhosis. There is 100-fold higher chance, 100 times chance for developing liver cancer if a patient is having liver cirrhosis. So it is, we cannot say it as a risk factor. It is a moderate. So even we can say diabetes also. Diabetes risk, we cannot simply use the term risk factor. It is a, this can be associated with the development of cancer.
Okay, thank you, ma'am.
Oh,
thank you.
Thank you so much. So I will.
You are leaving, or end of the session only? I think so. Thank you, madam, for your wonderful talk.
Thank you so much.
We are inspired by you. Thank you. Let us move on to the next session. Let us give a warm welcome. Next. Let us give a warm welcome to the speaker, Professor Anil C. Matthew, for the next invited lecture. Professor Anil C. Matthew of Biostatistics Department, Institute of Medical Sciences and Research, Coimbatore, is internationally known for his innovative teaching methods in biostatistics, including clinical epidemiology, multiple linear regression, logistic regression, and survival analysis. He has taught more than 200 courses worldwide and visited several countries, Sri Lanka, Kuwait, Bangladesh, Nepal, and Indonesia for sharing academic sessions and organizing short courses. In recognition of the eminence achieved by way of his outstanding contributions leading to the promotion of statistics in medicine, Professor Anil C. Matthew has been conferred on FSMS of the Indian Society for Medical Statistics for the year 2017. It is with immense pleasure inviting you, sir, for delivering the lecture on analysis of matched data using regression models.
Thank you, madam. And thank you, Sadish sir, for giving me this opportunity. Is it audible to see my PowerPoint?
Yes, sir.
Yeah. Audible and also visible. The PowerPoint is.
Yeah, thank you, sir. And it is, this is a motivational talk for the postgraduate students, which is a lot of debates are taking place on this particular topic. I just thought of highlighting some of the. I'm not going to share any of my findings, but just highlight what is this matched case control study, especially the researchers who are starting the early career researchers. I hope this PowerPoint and presentation may be useful for it. So basic features of matching. In case control study, we consider reference group as the controls and index group as the cases. In follow-up study, the reference group is unexposed and index group is exposed. And purpose of the matching is reference group should be comparable with the index group. We have one-to-one match to one control, we call it as one-to-one matching. And one case to R controls, we call it as one-to-R matching. And RI cases to RJ controls, we call it as RI to SJ controls. How many controls we have to select? That is the first question usually a researcher may ask you. We have Pitman's efficiency criterion, which it tells you variance of odds ratio 1:1 divided by variance of odds ratio R/1 is equal to 2R by R plus 1. If you look accordingly, the maximum efficiency what we are getting is 4 controls. After 4 controls, if you look, the percentage is increase is very small only. But up to 4 controls, we can see the increase in the percentage. So the maximum efficiency is only 2, but with the 4, we could get an efficiency of 1.6. There is little to gain in precision from choosing R to be greater than 4. Now, what is the meaning of why we need the unmatched analysis? Is there any problem for it? Let us take an example of a gray hair and stroke. The odds ratio is 18.15, but if you divide this into younger age and older age, the odds ratio remains the same thing only. Absolutely, there is no association neither in the younger age or in the older age. But when you pull the result, you can see a high odds ratio. This is actually what we highlight for the big fresh postgraduates. I can just tell you, this is the issue which what we call it as confounding. So what is a matching? Matching may lead to tighter confidence interval, more precision. But basically, the more problem with the matching, it is extremely difficult to find match. For a case with a 42-year-old Christian female to control of the same age, religion, and sex combination, it's very difficult actually. So usually we may go for the frequency matching. Now let us take a case control study as an example. Case controls. This is looking at a pairwise form. Here the first pair, case is exposed and control is not exposed. For the second pair, case is exposed and control is not exposed. When you look into this type of 20 strata, what actually happening is that there are certain strata, both the cases and controls are exposed. There are certain strata, case is exposed and control is not exposed. There are certain strata, control is exposed and case is not exposed. There are certain strata, both the cases and controls are not exposed. For example, the previous example which I told you, stratum number 3, both the cases and controls are exposed. Whereas stratum number 1, case is exposed and control is not exposed. Whereas in stratum 4, case is not exposed and control is exposed. Whereas in stratum 8, both the cases and controls are not exposed. The basic statistical analysis for the match data is Mendel-Hensel test or McNemar analysis. I put McNemar analysis or that is because both at the end you will get the same result only. Or when you have more than many variables, we may have to go for conditional logistic regression model. What is this Mendel-Hensel odds ratio? It will tell you. This is a formula sigma AADI by NI divided by sigma BICI by NI. You get an odds ratio of 2.50. And Mendel-Hensel chi-square is 1.79 and p-value is 0.118. So if at the same time, even if you do McNemar analysis, we will look how many pairs the cases and controls are exposed. How many pairs cases is exposed and control is not exposed. How many pairs cases not exposed and control is exposed. And how many pairs cases not exposed and control not exposed. In this situation, the odds ratio is B by C, which is 2.5. But what we can see, whether you do the first way or second way, you are going to get the same odds ratio only. Why? Because the reason why we are going to get the same odds ratio is out of these 4 combinations, when you do the first, this Mendel-Hensel odds ratio, when it comes for the numerator, only this particular portion alone will not get cancelled. Similarly, the denominator, when you look into it, this particular stratum 3 will not get cancelled. So if you have B pairs in that category and C pairs in the other category, automatically the odds ratio will become B by C. Now come for the conditional logistic regression. This logit P, for example, it's a exposure is smoking and outcome is coronary heart disease. The simple logistic regression model, the model is logit P is equal to coronary heart disease, which is equal to 1 as a function of beta naught and beta 1 smokers. But at the same time, if you wanted to do this conditional logistic regression analysis, because there are 10 strata are there, and the last strata we have to consider as the reference category, we have to create dummy variables for the next the 9 stratas. So accordingly, the logit model will become beta naught plus beta 1 smokers plus gamma 1 into VA, I going from 1 to 9. And we have to do the conditional MLA to estimate the parameters. For again, the freshers, I just explained you this concept, maximum likelihood estimation, what is called the conditional MLA versus unconditional MLA. So beginners, I just thought of giving a small explanation. The regression analysis, if you look into the, especially when the outcome variable is binary outcome variable, past versus present. discriminant function analysis was used to estimate the parameters. But when independent variables are categorical, what will happen is that discriminant analysis tends to give biased results, whereas logistic regression analysis requires no restriction on the independent variables. Now, when we come for the estimating the parameters, commonly we have two methods of estimating the parameters. One is called a least square estimation, other is called a maximum likelihood estimation. In classical linear regression model, when the dependent variable is normally distributed, whether you do least square estimation or whether you do maximum likelihood estimation, it doesn't make much difference. Why? Because what the least square is going to do, the least square, what it's going to do is, it will rotate the scale at various positions and measure the square of deviation from the point. And the point which is having the least value is called the least square regression. But why this least square is not possible in the logistic regression? The basic reason is that out of the 10 values in the x-axis, when you do the logit model, what will happen is that this deviation, when you measure the deviation and the square, it will become 0. So you can't use this least square method. It's used in the past as it requires computer programming. But then ML can be used for non-linear and linear methods. Logistic regression is a non-linear model, and ML estimation is the preferred estimation of the parameters. And the computer programmers for ML estimation for logistic model, SAS we have provision for it, SPSS we have provision for it, Stata we have the provision for it. Now let us make the concept a little more simple. Suppose if you have a trial of n 100 trials and P be the probability of success, and X is 75 success and n minus X is 25. The probability of 75 success out of 100 trials, it will be P. Then this P of getting X is 75 is C into P raised to 75 into 1 minus P of 100 minus 75. What the likelihood function represents, the joint probability of observing that, the data that have collected, the probability of observing 75 success out of the 100 trials using binomial model, but we need to estimate the unknown parameter P. The ML chooses the unknown parameter theta in such a way that maximizes the likelihood function. So simply what we should do, dl by dp, is to make it as 0 and solve the value for the P. For example, the same parameter is a very simple differentiation, only not a complicated differentiation. When we do this differentiation, what you will get P is equal to 0.75. The maximum likelihood value will get P 7.7. What does it give an ordinary person? When P takes any value more than the maximum, LP will be all the time less than LP of 0.75. That means even if you give a value for P1, LP value becomes only which is less than 0.75. So in a simple way, in binomial model, P is equal to X by N is the maximum likelihood estimator, and more complicated model, the complex calculations. Now come to the point, unconditional approach. This unconditional approach is preferred if the parameters are small compared to the number of observations. Whereas conditional approach is preferred if the number of parameters are large relative to the number of subjects. For example, N is equal to 700 and outcome is coronary heart disease, and we have an exposure factor E and covariates C1, C2, C3, C4, C5. Number of variables which can incorporate in this model is exposure factor, and for confounding factors, even if you put all the interactions C into C1, it only comes only maximum this much only. So it is a total variables is much lesser than the sample size. So there's absolutely no harm in going for unconditional approach. But on the other hand, when you look for a case control study, especially matched case control study, let E be the exposure. What will happen if there are 100 matched pairs? We have 9, as I told you, 19 and dummy variables we have to create for the 100 data. So the total number of variables will become 103. Conditional logistic MLE estimation. So what is this? What we are going to do in the conditional versus unconditional? What is the difference in the algorithm? Unconditional LU, the L formula are different for both the unconditional and conditional methods. Let us make the concept very simple. The outcome variable X takes value 1 or 0. We have the set of covariates and we have exposure variables. In unconditional algorithm, unconditional formula describes the joint probability of the study that the product of the joint probability for the case and the joint probability for of xi for each case into P of 1 minus xi, where I going from 1 to mi. And Px is asked in the form logistic regression. It is 1 by 1 plus e raised to minus alpha plus sigma beta I xi. Anybody simplify it at the end? So anybody can simplify this. What we are going to get by going from 1 to n e raised. This is the what at the end you will get in the unconditional estimation. But the interesting part of it, when you go for the conditional algorithm, what the conditional algorithm says is probability of first M1 cases divided by probability of all possible configurations. That means observed data is collected on M1 cases and N minus M1 non-cases. You have to see all the possible probability of all possible configurations. But that means first configuration can be first M1R cases and the remaining N minus 1 M1R cases. And second configuration starts with the second in the list and up to M1. Like that, there are total NCM1 combinations. So at the end, when you do this particular part of it, the interesting part is which you are going to get in the conditional algorithm is if you look into this formula, there is no alpha is not available. The alpha drops out from the scenery. This is a very important finding, especially those who are going to do match the case control study. This is a very important thing. One is the alpha is a nuisance parameter for us, especially when we do a case control study. But for a prospective study, alpha is a function of incident rate. So for that study, it may not have much issues. But when we do a case control study, it is a headache for us. So for a matched design, alpha is estimated under a conditional argument involved in the estimation parameters. So at the end, if you do this conditional logistic regression analysis, what the result which I get in this finding is smoking is equal to 2.50 is the odds ratio. And how to do this, the SPSS, I
Talking about matching in case control studies, and could you please explain, if possible, what is the difference between this and propensity score matching? This is just for understanding.
the propensity score.
Actually, I also asked to know about it because you are the right person to ask. Okay, we will learn together.
So give me one week time. Give me 1 week time. I just share with you. So give me 1 week.
Can I answer?
Yeah, Eliama, can you answer?
Now, this propensity score matched analysis nowadays we commonly use. In fact, it is exactly the matching. Randomly, we can match using computer. We can match. Propensity score programs are there. There are several options. The problem in propensity score matched analysis is sample size will be reduced largely. So for suppose we need to match age, exactly matching can be done using age, gender, or for cancer stage at diagnosis. Suppose there are say one stage group, so matching is done for obtaining a comparative group. So the mentioned what Anil mentioned about matching, it is 1:1 matching or 1:2 matching we can do. In the propensity score matching, that is done using computer. So matching will be there. Suppose there are 1,000 cases in our study and another say 2,000 controls, or control population will be large, say 10,000. So we can obtain using computer, using this propensity score, we can obtain matched controls. But we may not get matched controls for all our 1,000 cases. So sample size will be reduced largely. So if there is a large population, we can of course use propensity score matched analysis, and that will be, the results will be better than the other type of matching.
Thank you, Eliama. Clarified nicely. Sadish sir, next year, if you invite me, I will give the talk on propensity score, sir.
Thank you, sir.
Thank you.
Clear to you?
Clear.
No, the person who asked this question.
Yeah.
Okay. Thank you.
Any more?
No, I like that talk. I always listen him. So he's a good teacher, in fact. So that's why I just want to ask some question to clarify things.
Yes, sir, you are absolutely true. Thank you, Eliama madam, and thank you, Anil sir. Let me conclude. Shall I?
Thank you, the
I,
teacher.
I express my sincere gratitude to the chairman, Professor C. Satish Kumar, and Dr. Riyas for considering me eligible for chairing the session. I express my heartfelt thanks to the two eminent personalities, Professor Eliama Matthew, Professor Anil C. Matthew, for delivering a thought-provoking brainstorming session. I express my sincere thanks to Joe sir and all other eminent participants of this session. I extend my best wishes for the successful conduct of the seminar for the third day also. I am sure that WSTA 2024 will be a grand success and wholeheartedly congratulating the organizers of WSTA, especially my guide, Dr. C. Satish Kumar, Swapna, for inviting me to chair. Thanking you all once again. Thank you. Thank you for your patience.
Thank you, the teacher,
Thank you, sir.
Dhamma teacher, for your support as the chair to this session
Thank you, sir.
and managing this session in a very nice way. And also, let us give a big clap to the speakers of the session. Both have done a wonderful presentations. We are always grateful to Eliam madam and Manil C. Matthews.
Thank you,
Once
sir.
again, thanking you, process. Let us. In fact, we have 5 more minutes there to the next session. Is it correct? More than 5 minutes.
10 minutes.
So 10 minutes is there.
Yeah.
So I hope the next chair has not yet joined, but the speakers are there, I think. One of the speakers, Darba Professor.
I am already calling him. He
Okay.
joined very soon, sir.
Yeah. Please. Okay. By the time you can speak something, teacher can give some.
Good evening, Professor Darba Bhattacharya.
Good evening, everyone. Nice meeting you all. Yeah.
Evening.
Good evening, Satish sir.
Good evening, madam. How is things there in Calcutta?
Yeah, it has cooled down a bit. It was very hot, and now we are getting some showers. So
Wait for a few minutes. That's fine.
yeah, sure.
എനിക്ക് തോന്നുന്നു ഇനി ആകെ 5 പേരേ ഉള്ളൂ. 5 പേര് 9 മിനിറ്റ്. അപ്പൊ 10:30 തൊട്ട് 11:20.
How is Coimbatore, sir? കോയമ്പത്തൂർ ഇതുണ്ട്.
കോയമ്പത്തൂർ ഇങ്ങനെ പോകുന്ന പക്ഷെ നല്ല ഓഡിയൻസ് ഈ സമയത്ത് ഇത്രയും പേര് നിൽക്കുക എന്ന് പറയുന്നത് സംതിങ് ഗ്രേറ്റ്.
രാജഗോപാൽ സാറിനെ കണ്ടില്ലേ?
കണ്ടു.
പ്രൊഫസർ രാജഗോപാൽ I hope now you can introduce the chair and start the session. Okay. Bhagya?
Yes, sir.
Yeah. Please introduce the chair. Chair, I hope chair joined.
Yes, sir. He's joined, sir.
Okay. Please introduce the chair and initiate the session. Please.
Good evening, sir.
Good evening. Good evening.
Hello, everyone. We are moving on to the 23rd technical session of WSTA 2024, which is an invited session that shall be chaired by Dr. Devendra Kumar. Now, Dr. Devendra Kumar is a faculty to the Department of Statistics, Central University of Delhi. His areas of interest include distribution theory, generalized order statistics, and estimation. He has a lot of publications to his credit, including Alpha Logarithmic Transform Family of Distribution with Applications and Extended Exponential Distribution based on order statistics. We are fortunate to have you, sir, with us sharing the session today. On behalf of the organizing committee, I extend a warm and kindly request you to take over the session. Over to you, sir.
Thank you, Bhaglachmi. So this session, there are two speakers. First one is Professor Bhattacharya and second one is Baron Agrawal. Professor Bhattacharya from St. Xavier
Hello.
College, Kolkata. And her title is Bayesian Non-Parametric Development and Applications with a focus on digital process-based mixer models. So I invite Professor Bhattacharya to deliver her lecture. Over to you, ma'am.
Hello, am I audible?
Yes, yes, ma'am.
Yeah. So I'm sharing the screen. Is my screen visible?
Yes, yes.
Yeah, it's fine.
Okay. So good evening, everyone. I am Durga Bhattacharya from St. Xavier's College, Kolkata, and I would like to thank the organizers and Professor Satish for inviting me to deliver this session in the 9th International Webinar on Recent Trends in Statistical Theory and Applications 2024. My today's discussion intends to be an introductory discussion session on Bayesian nonparametrics, and focus being on Dirichlet process priors. We will try to understand why we need Bayesian nonparametrics and how we can manage to understand and apply it. Fine. So after discussing the development, I would like to discuss a few applications, particularly in the area of landscape classification of Western Ghats and human genetics. So this slide gives an overview of how this session has been planned. We start from what is Bayesian nonparametrics. We discuss the development of the Bayesian nonparametrics methods, focus being on Dirichlet process priors, and finally we discuss some applications. So any statistical problem solving, we start with data, which is a collection of random variables. And the statistical problem arises, so when we try to model this data using some probability distribution, G, capital G. So the statistical problem arises when there is some uncertainty about G, and how we deal with this uncertainty, it gives rise to various perspectives of how we want to solve the problem. So a typical parametric model, we have a parametric model when this class of distributions is indexed by a finite set of parameters theta. And we aim to use different, our sample to find out a plausible value of theta or to suggest a subset of theta which can possibly contain theta. So the problem with the parametric methods is we end up with very strict functional assumptions on the model, which might lead us to misspecification of the statistical model. For example, if you consider this panel on the right-hand side, so if you want to model this data using sorry, is my slide available? Is it visible?
Yes, ma'am.
Okay. So if we want to model this using some functional form with a strict functional form, then we might miss what is happening at this corner, maybe. Or if we want to model this part of the data. So instead of assuming a strict functional form, if we can assume a probability distribution which is general in nature, that is, any functional form, suppose a general CDF or a general probability distribution, capital F. So by non-parametric ways, by non-parametric we don't mean absence of parameters. So it's basically if we have a general class of distributions, if we are looking for a general class of distributions which can define the probability distribution. So our problem is no more restricted to a finite set of parameters as in the parametric model. We are dealing with a large class of densities which can no longer be indexed by a finite dimensional parameter theta, and which gives rise to the problem of infinite dimensional space. So we are dealing with the infinite dimensional functional space. And what we want to do, we want to define a probability model or probability distribution on this infinite dimensional functional space, which gives rise to the problem of Bayesian nonparametrics. So how to define probability model on the functional space is what we will try to discuss today, and we will try to discuss some applications of this thing. Now, Bayesian parametrics has been around, say, now over more than 100 years. So with the introduction of modern computers post 1975, so it showed a significant hike in Bayesian parametric methodologies. So in Bayesian parametrics, what we do is we start with by jointly modeling the parameter and the data. We augment the sampling model, that is our likelihood, using the prior, and we derive a posterior distribution for theta. Now, there are different ways of summarizing the posterior. It's very widely used. Now, what is Bayesian nonparametric? So, we all are familiar with frequentist parametric approach, which mainly focuses on different methods like maximum likelihood estimation, etc. We all are familiar with frequentist non-parametric methods, which is based on methods based on ranks, or which are based on very general assumptions on the functional form of the probability distributions like continuity and all. And we are familiar with the Bayesian parametric methodologies. So whatever doesn't fall in these three categories falls in the category of Bayesian nonparametrics. So Bayesian nonparametrics models and methods are typically characterized by infinite dimensional parameter spaces, which can be considered as the unknown CDF or density or regression functions or link functions, or in some clustering problems where the number of clusters it can grow with the or number of parameters which can grow with the data. Like in the case of suppose modeling the species, so we get to know different species every week. If we Google, we can find that every week new species are being discovered. So, or if you are dealing with human networks, we know that these are the different networks which are available, but it grows with time. Or we are dealing with topic modeling. Suppose we have some idea about the topics which are currently being dealt with, but the number of topics or possible topics, it can grow with time. So such problems where the number of parameters can grow with time, or models which are defined on a class of functions which cannot be defined by finite dimensional parameter spaces, they pertain to problems of infinite dimensional parameter spaces. So construction of probability measures over infinite dimensional parameter spaces comes under the Bayesian nonparametric paradigm. So the development of Bayesian nonparametrics. So our argument for using Bayesian nonparametric methods, we will use different examples to support why we will need Bayesian nonparametric methodologies. So we start with a few examples. Like this is an example where if this So if we have a multimodal distribution in this way, and we try to model this data set using some restrictive functional forms, what we can see, this type of modeling, it doesn't allow for multimodality or skewness. But if we consider the class of all possible density functions, and we define probability models on it, we can see that this type of modeling, it can deal with such problems of multimodality and to a better extent. Okay. So if we consider this problem of T cell counts, so T cell receptors, so we can see that this data, it consists of 55 distinct T cell receptor sequences. So in this example, we can see that so T cell receptors, the count of T cell receptors is an indicator of immunity of a person. So we can see that this count frequency corresponding to the count 0, it is 0 here. So maybe that is the problem of the sample. So if you want to model it using some known probability measures, probability models like geometric or Poisson, what it will do is it will give a deterministic estimate of this unknown function. So instead, if we can consider a generic probability function which can model this data, in that case, what we will require is to define a probability distribution over this class of unknown functions f. So this can no longer be defined under the finite dimensional parametric setup. So this is an example which shows a semi-parametric model which can be modeled using Bayesian non-parametric. So in some cases, so infinite dimensional parameters, suppose theta 1 and theta 2 are there, where theta 1 is a q-dimensional parameter, which is a parametric component, and theta 2 is an infinite dimensional parameter, which is a non-parametric component. For example, if we consider a proportional hazards model, in that case, this lambda t given z, this is a baseline hazard function, which is infinite dimensional and can be any positive function in t subject to regularity conditions. Where this vector beta, this is a q-dimensional vector of regression coefficients. So this is a finite dimensional. So this is an example of a semi-parametric model. So we consider, so theta 1 is finite dimensional and theta 2 is lambda naught. So this kind of a problem where the parametric space is RQ cross S, where S is an infinite dimensional space of all non-negative functions on R plus, can be considered to be a semi-parametric model. So what are the challenges of Bayesian non-parametrics? How to define priors on functional spaces or infinite dimensional spaces. That is the first challenge of Bayesian non-parametric problem, because as we all can understand, defining priors on Euclidean spaces was much easier. So what we need to do is we need to develop well-defined probability distributions on these infinite dimensional spaces. Secondly, mathematically, it will be difficult to construct priors with large support, and practical difficulties in calculation of the posterior, which is very obvious. So nowadays, with the availability of software packages and implementation of algorithms, it is practically feasible to do the complex calculations which are involved in Bayesian non-parametrics. So it has found widespread applications in different areas like finance, geosciences, botany, genetics, etc. So we will consider a few such cases. So if we come to the density problem of density estimation, as we all know, in frequentist non-parametric CDF estimation, if we want to estimate the density, so from frequentist point of view, so how do we estimate the CDF non-parametrically? We do that using empirical CDF. And by DKW inequality, we know that probability of capital F lying between this limit, it is greater than equal to 1 minus alpha for some fixed alpha. So what is the non-parametric? So what is the Bayesian non-parametric counterpart of CDF estimation? It was given by Ferguson in the year 1973. It is, so if we come to the Bayesian non-parametric CDF estimation, so basically we need to understand that we have a space of all possible CDFs or functions F. So this space is firstly infinite dimensional set, and each point in this space on which we want to develop a probability model, it is a CDF or a function. So what we need to do is in order to proceed using Bayesian methodologies, we need to have a prior on the infinite dimensional functional space, a capital F. And secondly, once you have data and the prior, we need to combine this information to generate a posterior distribution. So how is that possible? And thirdly, what are the properties of this posterior? These are the important points which we want to touch upon. So the main problem in this development is that this, as we all can understand, this defining priors or posteriors on such infinite dimensional space, the interpretation becomes a bit abstract in nature. Okay. So to start with, we consider the finite Gaussian mixture model. We can see, so the problem of clustering, suppose we have two clusters and the data is generated according to, suppose, normal bivariate normal model, where Zn is the categorical variable. So there are two clusters, we don't know the observation. So we need to have some idea about what is the proportion of observations coming from both the clusters. So we can have a categorical distribution over rho 1 and rho 2, where rho 1 is generated according to beta A1, A2, and rho 2 is 1 minus rho 1. And the clusters are defined by the midpoints, mu k. So these are the parameters, mu 1 and mu 2. So mu k is assumed to be normal with parameters mu 0 and sigma 0. So this is a typical problem of finite mixture models. Now, the use of beta, so beta distribution is very appropriate for modeling rho 1 and rho 2 proportions here, because beta observations come in the range from 0 to 1, and it gives a conjugate prior to this system. So as we know, the beta distribution, depending on the choice of alpha and beta, we can have different types of choice of beta distribution according to our need of the problem. Now, if we have finite Gaussian mixture model of k clusters, suppose here in the diagram we can see 3 clusters. So we can have the multivariate extension of that problem, and the beta distribution will be generalized by Dirichlet distribution. So the proportion of observations coming from different categories, we can model it using Dirichlet prior, and the different labels are generated according to categorical rho 1, rho 2, rho k, and the observations are generated according to this normal. So this is a very common finite Gaussian mixture model which we can consider. And as we know that Dirichlet distribution is the multivariate extension of beta distribution, and just as in case of beta distribution, the choice of A1, A2, AK, it determines whether the Dirichlet distribution is concentrated along the vertices, or it is concentrated, or it will have a mode. Now, all the problems which we have discussed so far, if we notice the problems, all the problems in this problem or the problem before, we knew how many clusters are there. So we had an idea that 3 clusters are there or 2 clusters are there, and we are proceeding to model the problem or model the or define the generative model. Now, what if so far, whatever examples we have considered, the number of clusters was much less than the number of observations. So what if this is not the case? Like in the case of species modeling, where a new species is being discovered every week. Okay, so in such cases, the number of observations or number of clusters, we have no prior idea about how many clusters will be there, right, in advance. So in such cases, what will happen if we generate, so if there are suppose 1,000 clusters, for example, there can be infinite number of clusters. We might not know the number of clusters which exist. So suppose there are 1,000 clusters, and we have observed only, we have the number of data points is only 100. So we can have at the max 100 clusters or less than 100 clusters. But how do we fix the number of clusters in advance for the modeling? So how to choose the number of clusters in advance? This is the problem which is there in the classical clustering methods, and which is taken care of in the Bayesian non-parametric problem. So we now proceed to develop the Dirichlet process problem. So how to choose K in advance? How to understand or how to choose K in advance? So for that, we have to understand the construction of this Dirichlet distribution. So if we consider rho 1, rho 2, rho k to be following Dirichlet distribution with parameters a1, a2, ak, Sethuraman gave this. Then, so what is remaining is this portion 1 minus v1. From what is remaining, if we generate v2 according to beta with parameters a2 and a3 plus a4, and we call rho 2 as v2 proportion of what is remaining. So v1 is rho 1. So this is how we can generate a Dirichlet, an observation from Dirichlet distribution. And what is rho 2? Rho 2 is v2 proportion of 1 minus v1, what was left. So now what is left? 1 minus v1 times 1 minus v2 is left, right? So next we draw v3 from beta, a3 and a4. And we call rho 3 as 1 minus, so rho 3 will be v3 proportion of what was left, that is 1 minus v1 and 1 minus v2. So rho 3 will be this thing, right? And finally rho 4 will be 1 minus rho 3. So this method is known as stick breaking method, and this we have considered for a finite dimensional Dirichlet distribution, and this concept can be extended further to generate infinite k is equal to infinite probabilities that can add up to 1. We will see how. So based on this construction, Griffiths, Engine and McCloskey, they proposed the GEM distribution. So they were basically geneticists, and you can see that so the problem with this construction is how to choose A1, these parameters, A1, A2, A3 and A4. So the GEM distribution proposed by Griffiths, Engine, and McCloskey, they fixed these parameters as 1 and alpha, beta 1 and alpha, right? So for any k, no matter how large k is an integer, so they propose this method of generating. So v1, rho 1, rho 2, rho k, all these are, you can understand. So these lie between 0 to 1, right? So this is a typical draw which I have shown for GEM distribution for alpha is equal to 3, right? So for any choice of k, you can have this kind of distribution over 0 and 1. Okay. So for alpha is equal to 100, we can see the density it has become more dense. For alpha is equal to 3, the distribution, so it becomes more concentrated for alpha, for higher values of alpha. So Sethuraman provided this stick breaking representation. So in 1994, so we can understand that Bayesian nonparametrics is a very young field till now. It's not that popular because of the abstract nature maybe, but it has huge possibilities of applications, which we plan to discuss now. So basically, what is a Dirichlet process? A Dirichlet process is a probability distribution defined over the CDFs, the function capital F. So we assume that this probability distribution is a random probability measure generated according to Dirichlet process with parameters alpha and G naught. So like when we define probability distributions over finite dimensional spaces, suppose we have used, like, suppose X follows normal with parameter mu and sigma, where mu and sigma both are real numbers. Now, in defining Dirichlet process, this alpha is the concentration parameter of the GEM distribution. So this is a number. And what is this G naught? This G naught is a distribution. So Dirichlet process is basically a random probability measure over functions with parameters, two parameters alpha and G naught. Alpha is a real number, which is a concentration parameter of the GEM distribution, and G naught is a random probability distribution. So using this GEM model, we can actually generate a random probability measure over these functions. How, we will see. So it involves two steps. So what we will do is, I'll just summarize it. So the steps are, draw a collection of samples VI from beta distribution, from beta 1 minus alpha. That we have seen how to generate this deterministic transformation. And we can transform these to produce the weights PIs. And these atoms, M1, M2, M3, these are generated according to the base probability measure, capital G naught, right? So in order, so we can see that Dirichlet process it generates a random probability measure. As is evident from this diagram, that it is a discrete probability measure. Fine. So basically, Dirichlet process is a random probability. It is random probability distributions. It generates a random probability measure which is discrete in nature. So what is G naught? G naught can be taken as your prior belief on what the underlying distribution on the functions may be. And what is alpha? Alpha signifies how the strength of your belief. We will see. So these are, I've used R to generate these distributions. So you can see, so G naught, the base probability measure, I have taken it as normal 0, 1, and alpha I have taken to be 2. So we can see that so for small alpha, the stick lengths are longer. So as a result, what will happen? There are fewer significant mixture weights, right? And as I keep on increasing the alpha, the base measure remaining the same, we can see that the stick lengths are shorter, and therefore we have more significant components spread over the entire range. So with alpha is equal to 20 and the same base measure, we can see we have more significant probability. So this is a so Dirichlet process generates a discrete probability measure over the different atoms generated according to your uh, base probability measure G naught. So although your base probability measure is continuous, the random probability measure generated according to Dirichlet process will be discrete. So, so Dirichlet process is basically a prior distribution over the space of all probability distributions. So if it is a prior, so it is a probability distribution. So just like all the probability distributions we are familiar with, we deal in the parametric setup, there will be an expected value. So expectation of capital F G naught. So on an average, so you're defining a Dirichlet. So we assume that the data is generated according to a random probability measure capital F, which is generated according to Dirichlet process with parameters alpha and G naught. Right? So, so the draws. So if we draw from this Dirichlet process, we will have a probability distribution. So the observations from this Dirichlet expected probability measure. And variance, if we look at the expression for variance, we can see that larger the value of alpha, smaller is the variance. Okay. So if alpha is mean, it is more concentrated. We can see. So under parametric base, what we have done is we define a prior on the parameter theta, and we augment the likelihood with the prior, and we get the metric base also. We have defined here the augmented with the likelihood. So we here also we need to get the posterior distribution for the probability. So so how to get the posterior distribution under Dirichlet process prior? It can be shown that Dirichlet process prior is a conjugate prior. So if the prior is Dirichlet process, the posterior will also be Dirichlet process. So just a minute. So this is a schematic diagram. I'll just wrap up what is the usefulness of Dirichlet process priors. So we can see that
His title talk is
11 2022 estimated national state level incident development CDC between 2000 to 2021. Despite India become one of the largest contribution to the measures burden, crucial epidemiological information is significantly lacking. To mitigate this, the government of India has implemented various strategies to control or eliminate the measles. So the measures is to target the first dose measles vaccination, which is achieved more than a 90%. Also, the government is introduced the second dose of vaccinations regarding the measures to control the measles cases for the fatality as well as death. So other things is the implementing of the rigorous surveillance measures supported by sufficient laboratory resources. Others, what the government is introduced some surveillance system is supported by different location to control to measure the outbreak of measles and ensuring appropriate measurement of identified cases. Whatever methodology I have to use, the first is a study setting where I have to do this study. Monthly aggregate measles cases that of child immunization 9 to
Dr.
11 months
Varun.
with the first dose measles. Yes,
Your slide is not
yes,
moving, not move.
not
So
move.
please,
Okay.
yes. Please take the slide in show slide
It
mode.
takes slide mode is there. Maybe it takes little bit time. It is matters. Now it move.
Yes,
Yeah. So what type of what are we setting? Because we have to go for the Indian setting, we have to consider the every state or every union territories to getting the complete database of measles cases and death. So here we can take in the monthly aggregate data which is reported in HIMS. Health information system is available at an Indian level. Also the IDSP integrated disease surveillance system is also reported the number of measles cases and death. To where I have to take in the data from the measles cases. So there are two sources I have to consider. First is the HMIS, second is the IDSP data to capture the measles cases and death. For the child immunization, that means the coverage of vaccinations, I have to go for various sources of reports in state level as well as national level, and I also go for a sample surveys where the vaccinations informations are available. Apart from this, I needed the population coverage. How much population is there? Because the census is conducted in 2011. After that, no census is there. So we need a complete information regarding the population. How much population are under cover, under vaccinated in the age group of 0 to 5 years. So we have to project the population also based on the 2011 census and making a standardized age specific population information. So these three things are we have to consider to getting the informations for the measures as well as the vaccinations. Then after getting this data, because data is very unclean because of the so many multiple sources I have to use to capture or record the information. So I have to make a standardization validation of the data. So in this database, so many informations are missing, which maybe I have to exclude it. Some of information are not be appropriate. So I have to exclude it from the study. And some data is not available for some UTs. So I have to exclude it from this also in the analysis. Then I have to go for data management. Data management, we have to go for the aggregate monthly data into annual database to see the trend, how the trend is going on. Then I have to calculate the annual incidence rate per million, case fatality rate, measles vaccination coverage in conjunction with the population estimate. In the data analysis, first I have to develop the what is the incidence, case fatality rate, and measles vaccination coverage at national and state level. Then I generate a trend plot with a bar graph displaying annual incidence rate and vaccine coverage, and develop a multi-level fixed effect panel model to estimate the measles incidence rate. This is a model I have to consider to predict in future when the India is under the control of measles cases. So this are first these are results are there. In table one, we have to report the in every year which state having a highest number of cases and highest number of deaths, and what is the case fatality rate for every year. If you see, most of the cases are highly in West Bengal or Uttar Pradesh every year. But the debt, if you see, the debt is not much high in the West Bengal and UP. It may be somewhere the multiple states are there, or some south state, the Andhra Pradesh is there. Then the Gujarat is there, where 2019 and 2020, the multiple states are there. But if you go for a case fatality rate, in the starting time of 2011, 2012, the case fatality rate is increased towards to downward trend up to the 2014. Then onwards, there is a increasing in the case fatality rate. That means the death rate is increased. That rate due to the measles is increased, which may be the alarming for the government to control the death among the measles cases. Then we have to see the what is the annual incidence rate of per million and the measles vaccination coverage. If you see the annual incidence rate from 2011 to 2020, it may be reduced a very frequent, it may be speedily reduced, but it may be reciprocal. If you see, the vaccine coverage is going to the increase. That means there's some relationship exists between the number of cases and the measles vaccination coverage. So number of cases is decreased as the vaccination coverage is increased. But there's a downward trend in 2020 because of that, due to the unreported information regarding measles. Because that time there's a COVID impact is there. Today the reporting system is not be sufficient to report the measles cases. Then I have to go for the state-wise. How the state-wise variation is there in the incidence rate of measles cases. If you see in this heat map plot, if you see the north is having a starting 2011 to 2015, there is a high incidence rate in the northeast state, followed by the west is there, where the Daman Deep is having a highest annual incidence rate. So after the vaccination coverage is increased, there is a decrement in the measles incidence rate after the 2016 onwards up to 2020. This is the bar which is reported, the dark color is reported the higher number of cases, and the less color is reported, light color is reported the less number of incidents. Similarly, we have to go for a measles vaccination coverage. How the vaccination coverage is changes among the infinite, 9 to 11 months database. So the color is light, it shows that the vaccine coverage is very less. As the coverage goes to light form, that means the coverage is more. If you see in 2011, 2000, up to 2016, there is a less coverage of vaccination in North States. Similarly, if you see the cases, annual incidence cases among the North State is higher as compared to the other regions. So similarly here, because of the vaccination coverage is less, there is a high chance.
Whether the slides are moving or not, please.
Maybe this takes time to move this slide. It takes time to okay. So what is happening in these two figures? If you see, the Northeast state having a high incidence rate, and the vaccination coverage is low. So that means there's an inverse relationship exists between the vaccine coverage versus the incidence rate among the state also. So less the vaccine coverage, more the chance for incidence rate, as you see in the northeast state. Among the other regions are. Then we can see the case fatality rate. In the starting years, in the 2011 to 2016, the case fatality rate is very low in most of the states apart from the Haryana and the Maharashtra and Gujarat. But after 2016 or 2017 onwards, the case fatality rate, that means the mortality rate is increased. This shows a alarming sound for the government. We have to control the cases. Cases can control, but the death rate is increased. What is the reasons behind this to increase the death rate? Because of maybe the tracing of the cases is maybe the late reported. This is one of the reasons which may be happening to increase the case fatality rate data. Then we have to apply the panel data model to identify the relationship between the vaccine coverage versus the incidence rate. There are some other factors also there, but due to the lack of the information for the cases like gender wise or age wise, this is not be reported. So we only focus on the how the
Dr. Varun,
relationship between the yes.
please make the slideshow mode.
It is okay. It is moving.
Yes, slide is moving, but not slideshow mode.
The slideshow mode maybe the is a problem in the slideshow mode maybe. So what the table to summarize the finding of panel data analysis that explore the association between the measles vaccine coverage over the preceding 5 years and the incidence and the incidence of the major cases per million children population under 5 years of age. The coefficient in the table represent the estimated effect of a 1 unit change in major vaccine coverage on the incidence of measures, accounting for different model specification and holding other variable constant. In the fixed effect model, only time effect suggested. A 1 unit increase in vaccine coverage is associated with a decrease in 9.1 measles cases per million children 0 to 5 years of population. That means if the 1 unit changes, that means if the reporting of vaccine coverage in 90%, then there is a decrement in the incidence cases in 9.1 measles cases per million children. Throughout this effect will not be statistically significant. Overall results suggested negative associations. 1% increase in measles vaccination coverage during the past 5 years is linked to a corresponding decreasing in measles incidence. The random effect model suggests a small effect of vaccine coverage on measles incidence compared to the fixed effect model, indicating that the sum of the variation may be explained by unobserved factors specific to each state. The R-square value indicate the proportion of variation in measles incidence explained by the model. A higher R-square value suggests the model with both time and geographical effect explain more of the variation in measles incidence compared to the other model. Based on this expected model, if current measles prevention strategy and the vaccine rate of more than 93.5%, 94% are maintained in the upcoming years, the national measles incidence is predicted to reach zero by 2025. However, this prediction is based on the assumption that the vaccine coverage remain constant and other factors influencing measles transmission remain unchanged. Because what is happening, because we have only considered the vaccine coverage, but some other factor is also responsible to increase the to decrease the measles incidence rate, which we have not considered because of the lack of the data limitation. So what are the limitations we have to see? What are the limitations are there? We expected an underreporting the measles cases that as a coverage of the HMIS data for the private sector is unclear, because when I go for the HMIS database, it is mostly reported the public data. The methodology is not clear. they include the private sector information or not. So one of the reasons what are the outcome is coming maybe the underreporting. Then hence the both incidence and case fatality is also expected to be underestimated than the actual one. The incidence is also expected to alter marginal as we have assumed a fixed growth mode rate, because what we have to assume is the population having a fixed growth rate for the projection also. So there is a one of the assumptions that the population is not the fixed, it may be the changes during the time period. So analysis again little bit making a not a unclear reporting, or also during the COVID they less reporting 2020. So this is one of the reasons which may be considered to accurate your model as well as your assumption. So your analysis reveals a declining trend in major cases since 2014 in India, highlighting the impact of vaccination. However, fluctuating deaths and arbitrary increase in mortality underscore persistent challenges in the nation. National and state level commitment to enhance immunization across booster public health infrastructure, implementing innovation are crucial for a major-free nation. Still, effort and collaboration for stakeholders are imperative to achieve and maintain optimal major vaccination rate in India. Thank you.
Thank you, Varun, for a nice presentation. So the session open for questions. Please, any query or any suggestion? I think no one. So thank you, Varun.
Thank you.
Satish sir.
Yes, yes. Okay. I'm waiting for your response. Yeah, that's right. Let us give a big clap to both the speakers.
Yes.
Yeah. Both very informative and very wonderful sessions. Yeah. Both have done their different way of approaches. They are very good and useful to the researchers and youngsters also.
Yes.
We utilize this occasion to extend our gratitude to both of the speakers, Professor Dr. Darba Bhattacharyya, Madam, and Varun, Dr. Varun, for your nice deliberations. Also, we wish to extend our gratitude to the chair, Devendra Kumar, Dr. Professor Devendra Kumar, support. Okay, thank you so much.
Thank you, sir.
Thank you. Very much
Good day.
thankful. Also, Rajagopal sir is here in the group. Several are there, including Professor Gupta and several Professor Mohan sir, and several are there in the group now also to support us through their presence and nice words and nice and their blessings, in fact. Now, let us conclude today's session. And tomorrow morning at 9 itself, we will begin the session with Professor Barry C. Arnold, the first speaker of the session. And tomorrow also there are several good, excellent talks we hope to have. Professor Kusumovsky also will be there. Anyway, I utilize this occasion to thank and extend our gratitude to each one of you on behalf of the organizing committee of this international conference webinar.
Thank you, sir. Thank you. Good night, sir.
Good night, all of you.
Bye. Good night. Good night, Radhika. Yeah. Good night.
Thank you. Good night to all. Thank you.
Bye. Goodbye. Good night. Bye. Okay, let us meet. Thank you, Saktive, Professor Saktive. Let us meet.
Okay, sorry. 25 B ഇട്ടാ മതി. 28 അല്ല.
Thank you all. Thank you all. Thank you so much. Bye.
Thank you.
Good night.
Thank you, sir.
25.
Good night.
മറ്റേത് മാറ്റി വെച്ചില്ലേ നമ്മൾ? അത് വേണം. പക്ഷെ അത് ഇനിയിപ്പോ ഈ ദിവസം ഇനി നടക്കുമൊന്നുമില്ല. ആ
you.